Okay, so today is other good news, bad news day. So you want to be homework tonight, is Isaac was quite excited about. So,
I'm never excited.
huh?
I'm never excited. I'm just so
But how are you tonight? So today we're going to kind of go through the manifestation of these four forces and do some demos and kind of show you how all that works. So historically, okay, and to really, oddly enough, to really understand the four fundamental forces, you need to understand history, okay? And so, even if you look at like the history of gravity, which you would think wouldn't have that much of the storied history, it actually does. So for a while, they thought gravity was magic, okay? And you're sitting there going, oh, well, how can gravity be magic? Well, here's a simple idea, is if I take this rubber stopper and I drop it and it falls, what do you all say it is?
Magic.
Or gravity, whatever the case may be. Because, but now, is there anything, can you see anything directly touching the stopper?
No.
No. Okay? Now, if I put this down, and I put my hand up here, and it fell upwards towards my hand,
Magic.
that's magic.
No, that's the force.
So if it falls away from my hand, oh, that's just gravity, even though you can't see anything acting on it. But if I let go of it and it falls up, oh, you're a witch, burn him at the stake, or he's a Jedi. Okay? So in both situations, the object moves without any noticeable force. In one situation, it's one of the fundamental theorems of physics, and it's gravity, and the other one, it's witchcraft, all depending upon which direction that it goes. So you can see the basis of why they thought gravity was magic, because it makes it accelerate, but yet there's no noticeable force acting on it. So you go to the Aristotelian view of motion. So Aristotle had two different views of motion. What happens on the earth, okay, which was the natural state to be at rest, okay. Isaac wants to drop tennis balls all hour and watch what happens, okay. We know what's going to happen there, not rocket science. It's going to come to a stop. Everybody knows what's going to happen. There's nothing to discover. But Galileo comes along, the upstart pizza-eating scientist, and he says, whoa, 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 let's talk about this. And he says, well, imagine if there wasn't friction. Like you take this ball and I roll it, and it pretty much rolls all forever. Okay? It rolls a long time before it slows down. So Galileo shifts the perspective after 2,000 years, literally from about 400 BC until about 1600. So for about 2,000 years, while okay, hey, things just come to a rest. Galileo says, no, they only come to rest because of friction. So Newton takes that law and he says, okay, I'm going to basically steal Galileo's work and make it my first law of motion, which basically says that whatever state of motion an object has is whatever state of motion that it wants to maintain. But there's something very specific about it. And that's the idea that motion in a physics classroom is defined as being a vector. So a velocity vector has two things. What does it have? Magnitude and direction. So if you talk about the magnitude, okay, that's just how fast you're going. So if you're going to slow it down, speed it up, do whatever, that requires a force, which is what happens when you drive your car. You press down on the gas pedal to make the velocity vectors get bigger. You press down on the brake to make the velocity vectors get smaller. Okay? So that requires a force to change either one of those vectors. You turn your steering wheel to change the direction of that. So Mother Nature says, look, I'm not into changing velocity vectors. I don't want to change the magnitude. I don't want to change the direction. If you want to do that, that's on you. Cool. So that was a huge shift from Aristotle's view that says, oh, things come to a rest. Newton says they only come to a rest because there's friction. You alleviate the friction, things keep moving. then that rolls into the second law that says F equals ma. Oh, okay, right? Well, now that we've introduced this idea of forces, what's the relationship? And Newton says, that's just F equals ma. So if you want to create that acceleration acting on a mass, the more force that you apply, the bigger the acceleration is. And that's what every time you drive, every time you hit the gas pedal, every time you hit the brake, you are subconsciously using F equals ma, because you're not changing the mass of your car. That's kind of a fixed value. It isn't like, oh, I want to go faster, I'll throw off a bumper. No, okay? Mass is kind of a fixed value. So what you decide is how much force that you apply, and then that determines your acceleration. Oh, hey, I'm running late. I got to get to school fast. Boom, press down on the gas pedal. Okay, bigger force, more acceleration. Hit the brakes. Oh, there's a squirrel. I like squirrels. Okay, hey, I'm going to stop, and I need to stop quickly. Versus, hey, I ran out of gas. I want to coast, so I want to have a small acceleration. Okay, so that's what you're deciding every time that you drive. That leads us to the motions of the heavens. So Aristotle had a different view of what happens in the heavens, okay? So if you look at the path of the moon, if you look at the path of the star, if you look at all of anything that's in the heavens, everything appears to move in circles, okay? Like this moon rises in the east and it sets in the west. The sun rises in the east, it goes overhead, sets in the west. All the stars tend to move in circles. So Aristotle had a separate set of motions for the heavens, and he says the motions of the heavens is actually circular because of the fact that that appears to be the path. So Aristotle had two views. On Earth, things come to a rest. You want to keep them moving, you have to apply a force. Heavens move in circles, and that was based upon observations, okay? You don't see anything moving straight across the sky. You see things moving in circles. So Newton takes it, hey, I'm not going to change the velocity vector. Now here's an example of how that relates to the motions of the moon. We'll talk about the moon in just a second. If I take this rubber stopper and I spin it around over my head, if I let go of it, what's the rubber stopper going to do?
Fly in the direction you let go.
Okay? It's going to go flying off, right? If Mother Nature liked circles, what would the object, when I let go of it, what would it do? It would be cool. It would continue to orbit around me. Okay, it's like, oh, this is cool. It would be. If Mother Nature was into circles, when I let go of it, it would just continue to go around like this, which would be extremely cool. Like I can walk down to the office. Wow, her camp, nice stopper, moving around. Right? But that isn't what happens. Because Mother Nature goes, whoa, I'm accelerating because I'm changing the direction of that velocity vector. And if you stop applying the force, it goes flying off. So Newton then applied that to the moon. And he says, okay, if you look at the fundamental force of gravity, and he came up with this equation, big G, M1, M2 over distance squared. Okay, here's all you need to know for this equation for now, okay? We'll spend a whole unit talking about gravity. The only thing I need you to know for now is that any two objects that have mass will be gravitationally attracted to each other. Okay? That's it. That's all you need to know for now. And the further apart those objects are, the weaker the gravitational force is. Okay? That's all you need to know for now. So, Newton looked at the big picture, and he said, here's the Earth, and here's the moon. Okay? So if you apply that same idea to me spinning that rubber stopper over my head to the Earth and the moon system, same idea. Only difference is the moon's a lot farther out. But Newton realized that just if I if I let go of the string, what does it do? Oh, it goes flying off. So by virtue of the fact that the moon is moving around the Earth, there has to be a force acting on it. Gravity! Okay, or there's a really long string. Okay, let's go with gravity. Possibility.
Could be magic.
Could be, or just magic, which don't discount that. So you've got gravity. So that's cool. Now, this is where this goes into Newton's third law. It's like, well, what does the moon have to do with gravity? It has everything to do with gravity, and it has a lot to do with Newton's third law. So Newton's third law, notice this is Newton's third law. This is not Newton's suggestions, this is not Newton's theory, this is not Newton's, well, kinda, okay? These are laws, which means they're invariant. So Newton's third law says, hey, for every action there is a reaction, or the idea that forces are coupled. I hit the table hits back on my hand. Now, this is where you have to look at a big picture and go, okay, here's the moon being pulled by the earth. Nobody has a problem with that. Okay, yeah, the earth is pulling on the moon, right? We're big, the moon is small, right? We're pulling on it, that's what allows it to stay in orbit, okay? But for this to be valid, if the earth is going to pull on the moon, what does the moon have to do? The moon has to pull with an equal and opposite force back on the earth, okay? Now, this is why we have tides. If you've ever been around the ocean, we have tides. And basically what happens is that gravitational pull creates a bulge in the ocean. And the earth is spinning through that bulge. So that water being closer to the moon is pulled in that direction. So there's a bulge, and then the earth basically spins underneath that bulge, which is why you have tides. So, and this is for every force, there is an equal and opposite force. Now, because of that force, hold on, I had a tennis ball floating around here somewhere. Anybody see a tennis ball? I might take it back to that. Can somebody, I need that, a tennis ball. Can you see if there's a tennis ball somewhere in the back? I can use Hank, but Hank's heavy. I was throwing it around. It's got to be somewhere. Okay, open up one of those drawers and see if there's a tennis ball in one of those drawers. Right there, no, right there. Look at those. I need a tennis ball.
There's baseballs and golf balls. Oh, it's next to the legs of your chair.
Just next to what?
The legs of your chair.
Oh, there it is. Never mind. Okay. Problem solved.
Keep it straight.
Got it? Okay. So, if this was like to scale, the tennis ball, to reference the actual distances, if this was the size of the moon, it would need to be about from the Earth, if I was the Earth, to scale, if this was the moon, it'd be about 10 yards away, which would kind of be like towards the back of the room, okay? That's, on scale, that's how far the moon would be. Now, here's the cool thing about the moon. So every once in a while, even as much as I've studied science and things like that, every once in a while you come across something that's like, wow, this is really cool. So let me give you a little background about the moon. So the moon is said to be tidally locked to the Earth. So let me explain what that sounds horrible. All that means is this, is that when you look at the moon, which is like this is the moon, let's say this is the side of the moon that says Wilson, okay? What that means is that as the Earth spins on its axis and the moon goes around the Earth, the same side of the moon is always facing us, okay? No matter what phase the moon is in, full moon, new moon, quarter moon, doesn't make any difference. The same side of the moon is always facing it. So that was the cool part of the Apollo 8 mission. The Apollo 8 mission was the first ones to orbit the moon. So those three guys were the first people in the history of civilization to ever see what was on the other side of the moon. Now, it's not necessarily the dark side of the moon, because it still goes through phases of sunlight and darkness. So it isn't the dark side of the moon, but it's the side facing away from us. So if you're on the moon looking at us, the Earth takes 24 hours to spin on its axis. So if you're on the moon, you would see every side of the Earth, because the Earth spins 24 hours. The moon takes 27 days to go around the Earth. That's also how long it takes to spin on its axis. So the orbital period of the moon is the same amount of time it takes to spin on its axis. So as it goes around, you're always seeing the same side of the moon. So here's the odd thing about this, and this is what I found shocking, is that it's a huge if. But if you lived on the opposite side of the moon, Okay, so if you lived over here on the side away from the Earth, you would never know that you're orbiting the Earth because you would never see it. You would know that you were orbiting the sun because you would have daylight and darkness. But if you lived on this side of the moon, you would never know that the moon is orbiting the Earth because you would never see it. And so that's kind of cool to think about. It's like, oh yeah, I'm on the moon. Do you orbit anything? No, we just go around the sun. Okay? It's like, no, you orbit a planet. No, I don't. Never seen it before. Okay? Now, if you're on this side of the moon that's facing it, you go, oh yeah, we see the Earth all the time. All the time. It's always there. Okay? But if you're on the other side, you go, hey, you orbit a planet. No, we don't. Never saw it before. Oh, here you go. So it's kind of a cool thing if you think about it. So, gravity. Here's all you need to remember about gravity. It's always attractive. More mass you have, the stronger the gravitational force is, but if you increase the distance, that becomes small. So, through about the early 1700s, 1800s, everybody was cool with gravity. They had that figured out. They were also able, at that point, to perfect more of the observations. So they could predict, like, the phases of the moon. They could predict solar eclipses, lunar eclipses. They had the physics thing kind of figured out. They understood Newton's laws of motion, F equals ma. And that time, in the early 1900s, the scientific community was kind of like dead in the water. They literally thought that they had everything figured out. They had the physics of gravity, they had the physics of motion, they had all of that figured out. The kind of nagging area was what happens on the structure of the world. What's the world made of? So, brief history again. So, John Dalton was the first one to come up with the working atomic theory. He said that this is going to be important. He said that all atoms are indivisible. Okay, not invisible, but indivisible.
What's the Liberty
Huh?
Justice from?
What'd you say?
I said Liberty and Justice from.
There you go. So, but you have to understand where the concept and the word atom comes from. So Dalton was also someone who had studied history. So if you go back to the ancient Greeks, Aristotle and company thought that there were 4 elements that made up the entire universe. Earth, fire, water, air. And it makes sense. Okay, here's the perfect story that justifies this. Let's say that you want to make a clay pot to boil water. Well, where are you going to get the clay?
Earth.
From the earth. Okay, you're not going to pull it out of the air like, oh, I'll make a clay pot. Okay, right? You're going to go dig in the earth. Okay, you got your clay pot. Oh, you need some water. Okay, where does water come from?
Water.
The sky. Okay, this is ancient Greece. Don't get catty. Go and you turn on the faucet. This is ancient Greece. It falls from the sky.
Get it from the river.
Okay, from the roof, whatever. Okay, it's going to come from something. Now, what are you going to use to boil the water?
Fire.
Fire. Where does the fire come from?
Fire.
Wood. Where does wood grow from?
Trees.
Trees. Where do the trees grow from?
Earth.
Ground.
Earth. Okay. Where do the trees need to grow?
Water.
Water and air.
Hold on, man.
Okay. You burn the fire. Okay. What do you get?
Smoke.
Smoke. Where does the smoke go?
In the
In
air.
the air. You boil the water. Where does the water go?
In the
In
air.
the air. Later on it rains. Oh, the water's coming back down.
From the air.
From the air. So it's not irrational. I mean, it's really not. Where do you look at everything in this room? Where did it all come from?
Earth.
The earth. Okay, we didn't get anything from the sun. Okay, Mars, anything like that. It all came from the earth. Okay, it did. That's where it all came from. So you had another group of people that were called the atomists. Okay, so here's an example of how the atomists view the world. So this is a piece of aluminum foil. And they said, all right, here's this aluminum foil. Cool. If I tear this in half, is it still aluminum? Absolutely. If I tear that in half, still aluminum.
Yes.
And I keep going, and I keep going, and I keep going. At some point, I'm gonna reach a point where I can't tear it anymore, and it's still aluminum, or still has the properties of aluminum. So the Greek word atom means indivisible. So the atomic theory is based upon the idea that atoms cannot be divided. Once you reach the atom, it cannot be divided any further. In other words, I can't tear this any further and have it what I have left, it still has the properties of aluminum. That's how they viewed the atom. They had no mention of electrons, protons, neutrons, nothing like that. They said, hey, this means indivisible. So when Dalton came up with his atomic theory, he basically revisited that Greek word, okay? Greek word atom means indivisible. So Dalton's atomic theory said atoms are indivisible. He also said that atoms combine in whole number ratios, which is still true. If you look at water, oh, that's H2O. Sugar, C6H12O6. Hydrogen peroxide, H2O2. You go down the list. You never see a formula of, H3 Cl7/8. Okay? You never have 3/4 of an atom. You never have 7/8 of an atom. You have a whole number ratio or you don't. So that supported the idea of atoms. So basically he says, look, atoms are just little Legos on a really, really tiny scale. And if you put those Legos together in one thing, you get a tennis ball. If you put them in another way, you get a squirrel. If you put them in another way, you get Isaac. Okay? Put them another way, you get Isaac's water jug. Okay? So all we are just different combinations of atoms. Okay? But we're atoms that know that we're atoms because we have a consciousness.
Especially atoms.
So that worked for a long time. Okay? Now the other thing that he also said, and we'll talk more about this later, is that he said that all atoms of the same element are identical. So he said all carbon atoms are the same, all hydrogen atoms are the same, all chlorine atoms are the same. They had no concept of isotopes because they didn't have the equipment at the time to realize that there are two different isotopes of carbon, carbon-12 and carbon-14. They didn't have the technology to sort that out. They just said, oh, all carbon atoms are the same. Now, that held for a long time, okay? But there was a problem, okay? So, and I briefly showed you this yesterday, so hey, look at this. So, if I put my hand right here, nothing happens. It's like, oh, that was cool. What happened? Nothing. But there's sometimes you can learn a lot from nothing happening. So, is there gravity between my hand and the balloon? Yes, my hand has mass. Does the balloon have mass? Yes. I could plug that into F equals big G M1 M2 over D squared. I could get a number. Do you think it's a very big number? No, incredibly small. But what we've known for quite a while is that you can charge things. The first thing they used was actually an element called amber. So if I take this and I rub it with the blanket, okay, and then I put my hand here, I can kind of do this Jedi thing. Or I can make it move with my hand. So obviously something has happened. This is what we call force at a distance. There's no direct contact between my hand and the balloon. There's a gap there. So whatever this is doesn't require a medium to be transmitted. Now, if I want to move this balloon, hey, I've got to touch the balloon, right? I've got to move it. But if I charge it, then I can make it move as a gap, or I can make it move. So it's like, something's weird happening. So at the time, they didn't know anything about the subatomic particles of electrons, protons, and neutrons. Because once you start down that road, then it gets really, really weird. Okay? So we briefly talked about this yesterday. So we're going to use chihuahuas as electrons We're gonna use St. Bernards as the protons, and we're gonna use sheepdogs as the neutrons. And the St. Bernards and the sheepdogs, they just chill out inside the nucleus. Okay, we'll get to how we knew about the nucleus. That'll be a story for in about 10 minutes. We'll get to how we knew the nucleus exists. So the chihuahuas are the little yippy electrons, okay? So what happened there, what I just did, is that when I took that balloon and I rubbed it on the blanket, a bunch of chihuahuas jumped from the blanket to the balloon. Okay, and later on you'll see how we know this. We'll talk about what's called an electric field. So this has excess chihuahuas. So I bring my hand close to it. There's my fingernail, there's my hand. And my hand is also made of atoms, right? And the chihuahuas that make up my hand, they go yip, 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 and they go running away because they don't like the electrons that are on the balloon. Okay, so all chihuahuas hate each other. Okay, they don't want anything to do with each other. But what's left behind is the St. Bernards, and it has a T in it, so that's a positively charged. The St. Bernards, however, like the chihuahuas because they're oppositely charged. So what allows that balloon to move towards my hand is the movement of the chihuahuas, because they don't like each other. But yet the St. Bernards, which remain behind, are attracted to them, so that's why it moves towards my hand. Now, you can also do this. So, maybe give this a spin back. So if I do this and I charge this one, and then I take the other balloon, I rub it. Now when I try and push them together, they want nothing to do with each other. Because the chihuahuas here don't like the chihuahuas there. But if I put my hand here, it moves towards them. But if I put the balloon there, it moves away from it. It's like, ah. So something has to be happening in between. What we figured out, and this even gets weirder, is that what's actually happening is photons. Okay, because every charge has to have like a charge carrier. This is actually happening because of photons. And you would think, man, photons produce light. But they also carry the electric charge. So when I do this, you have two electric fields that don't like each other. They meet in the middle and they force it away. This one, the electric field is pointed towards my hand and it becomes attracted to it. Okay, so Ava, stop that. Take that camera. Let's go to the back.